The PDA. Everyone has PDAs and phones and laptops. And
they use it to look at share prices.
Sorry, the users can.
They look at share prices.
Oh, they're all okay. Well, you can write. Okay. You can write software to look at share price if you want to. I did that for a while. My first company was a company that wrote stock market analysis programs. Actually, that's how I learned C.
I think free software is a very expensive hobby.
Why?
Because you look at how many Mercedes on the road and expensive apartments around.
Yeah.
People are chasing all these things instead of writing code.
Yes, but are they enjoying life as much? You know.
What do you expect living in a colony?
Yeah. Yes. That's what I say. Oh well. Yes.
Imagine if you can be immortalized in the OSS world.
Oh yeah.
That's more important.
Right. Yes.
You can be clear.
Anyway, we'll move on to another topic. By the way, please tell me just when you want me to stop. We can just all leave if you want to, or whatever. I don't mind. I think I'm probably over time a bit. So this is just my random musings slide with sort of random things to talk about. I've already talked about the power of procrastination and how it can lead to new careers. I've already talked about that a bit. But I thought I'd tell you briefly about the Minecraft story. And because it shows how the community responds to challenges. And several years ago, a long time ago on an island far away, there was a company called Minecraft, and they do paid testing. So companies can hire them to test their products and write favourable reviews of their products and then publish them. And that's what this company Minecraft does. And so Microsoft hired them to do a comparison of Linux versus Windows as a file server. Do you remember this? This was about 1997, 98, I think, around that time. Sorry? Web and file server, they did both. They did both Netbench and Netbench. Yeah. I was interested in the file serving part, strangely enough, because web benchmarking is really rather pointless, really, isn't it, when it comes down to it. How many companies have more than 100 megabit link coming into their computer and their offices? And
please can have it.
yeah. Anyway, there's many derogatory terms I hear about web benchmarking, but there's a web benchmark program in my junk code directory though, if you want. So Minecraft, so they did this file serving benchmark, and they used this benchmark called Netbench. And Netbench is the benchmark that you see in computer magazines comparing the speed of file servers. And it comes to mind as sort of the acronym for MIPS, meaningless indication of performance statistics, something like that. But it's not MIPS. So Netbench is this benchmark that existed, and they published this result. And it showed that Windows was much faster than Samba on Linux. Okay, so how would we respond to that? Well, the obvious thing we need to do is test it ourselves. The problem with that is that to run Netbench, you need a very expensive lab. At the time, it would have cost about $1 million American dollars to set up a proper lab, or maybe $500,000, something like that. Australian dollars, junk money. At the time anyway. So you had to set up like 128 Windows PCs. You had to somehow breathe magic into them to keep them all up. And then you had to have a gigabit infrastructure, and you had to have a big server, and then you had to have lots of management consoles and lots of power leads, and they all add up. And so we had no way in the free software community to reproduce this test. So we had no way of answering this challenge that Microsoft had laid down, that they'd paid for. And so that meant we had no way of showing people that we really aren't slow or fixing the problem. We suspected that we really probably were slow at those operations, just because we had never run that benchmark before. And so what we did was a couple of us captured a Netbench run, captured that to disk using a sniffer, and then we wrote a program that was able to replay those packets on the network, but on a single client. So you just have one machine or two machines. So you no longer need a lab of hundreds of machines. You can simulate their benchmark in a very, very simple way. And that meant instead of this program only being able to be run by people with $1 million lab, it can be run with anyone with their home machine, and that means it becomes accessible to the Linux kernel developers. We went one step further. We broke up the program. The problem with Netbench is it gives a number that's good for managers, but it doesn't give a number that's good for engineers, because it gives an overall result. It doesn't tell you how fast your disk subsystem is. It doesn't tell you how fast your networking is. It doesn't tell you how fast your protocol stack is. It says how fast your overall system runs. Where do you start? There's millions of lines of code to look at. Where do you start? So we broke up when we rewrote the benchmark, the emulation, we broke it up into little pieces. So we have 3 separate programs. We have Dbench that emulates just the disk I/O part of the benchmark. We have Tbench that emulates just the networking part. And we have Nbench or a Netbench emulator that emulates the whole lot. And so what you can do is you can separately tune each of the components, speed up each one. So I published these programs, made them available. I'll show you what they do. Let's run them. So I can run Dbench 10 or Dbench 20. Right, this does a simulation of a 20-client Netbench run, just doing the disk I/O and showing how fast it is, and that's it. Doing a real Netbench run, usually what happens is you schedule the run a week in advance, or you schedule it a day or two in advance. It's difficult to set up and run. You have like a lab maintainer who schedules runs and gets machine time. This you can just run whenever you want to. Much, much simpler. Now, when I then posted these programs to the kernel mailing list, and I gave them to, in particular, some developers that I knew were interested in performance work. So David Miller, Ingo Molnar, and Linus and others, and they were all able to run these programs themselves and determine what the problem was. Now, the interesting thing was we ran this on Solaris and Linux on x86 on the same hardware. All right? And we found an interesting fact. On Linux, Dbench was fast, but Tbench, the networking, was slow. On Solaris, the reverse was true. Tbench was fast, and Dbench was slow. And the overall result was almost the same. Solaris, on x86, on the same machine, got almost exactly the same overall result as Linux on that machine, but for different reasons. In one case, the file system was slow. In the other case, the networking was slow. So on Linux, what we needed to improve in particular was the networking. And so this is where David Miller came in. David Miller is a Linux kernel developer. And I hadn't met him until then. I hadn't met him until a couple of years later, in fact. But he was able to download the program and try it on his home system and then diagnose what was wrong. And he used a really common trick, a common hack for working out what's slow. He thought it might be because of locking, right? He thought it might be because on SMP machines, multiprocessor machines, there was too much contention for locks. What's the easiest way, do you think, of proving whether it's lock contention that is slowing you down? Turn off the lock. So you build a kernel that doesn't do certain locks, right? And it's not safe, of course. You don't do this on a production system. But if you take out the lock and the system goes much faster, you know that's the problem. You know what you need to redesign. And in particular, whenever the application was reading data from a socket into memory, as it was reading it from the kernel into user space using a routine called copy to user, that copies data from the kernel into user space, it was holding the big kernel lock, the lock over the whole kernel. So only one program could copy data from the kernel to user space at a time, only one process. So if you have 4 CPUs, you can only use one of them. Only one of them can be used to copy the data in the networking paths. So the trick was to remove that lock. And it went much, much faster. And so then it was a matter of discussing on the kernel mailing list how we can avoid this lock. And this was at the point that I realised that Ingo Molnar is close to genius. Because Ingo looked at it and he realised we don't need that lock. In fact, it's safe without the lock. And the reasoning was this. Whenever you're doing copy to user, the destination could be paged out. There must be a chance that there could be a chance it's paged out. If it could be paged out, then we could take a page fault while copying it. If you can take a page fault, when you take a page fault, you have to release the lock, any locks you hold, the big kernel lock, while you're waiting for the I/O of the page. Therefore, if the kernel has already been correctly programmed with the lock, then removing the lock must also still be correctly programmed, or there must have been an existing bug already. Understand that it's rather subtle. What he's saying is that if we already correctly handle page faults, and everyone agreed that we thought the Linux kernel did correctly handle page faults, then it must be that we can safely lose the lock during a copy, because we would lose the lock on any page fault. Therefore, the lock isn't needed. Isn't that interesting? I thought it was a brilliant insight by Ingo, absolutely brilliant. So, they patched the kernel to remove that lock, and the performance doubled. Much faster, much better. There were lots of other improvements. That some of the checksumming code got improved by Daydem. The point was we now had a tool so that all the developers could then improve the performance of this benchmark. So it wasn't just in the one lab, where a big company had access to this benchmark. Now it was everyone had access to it. And the end of this story is the nice part. There's a proposal which seems likely but not certain to go through, that SPEC, the benchmarking people who do the official benchmarking, they will adopt this code as the next official benchmark. And so the emulation will become the real benchmark in the future, which I think is quite nice. It's not a very good benchmark actually, but my excuse is that it was an emulation of somebody else's benchmark. So anyway, that's sort of how the community copes with challenges like that, by coming up with novel approaches to the solution. And the final thing I'll talk about is the barrier to entry curve. As a project ages, the quality requirements get much higher. So this is a warning. If you're going to join a project, it's easier to join a project, because the quality requirements have gone up with the age of the project. So if you join a very well-established project, there are better support networks for developers in more established projects sometimes, but the quality requirements are much higher, so the standard is much higher. It can be much harder to come into a project. So I've gone way over time, I know. Any final questions, or people want to flee? Run away? No? So you can get a copy of these slides there if you like. Very welcome to grab those and if you want them. Otherwise, thank you very much for listening.